Hello and welcome to Migrating Databases to Amazon Aurora as part of the AWS Innovate Online Conference. My name is Blair Layton and I'm the Business Development Manager for Database Services in Asia Pacific. I'll be taking you through an overview of how to migrate databases to AWS today with a focus on Amazon Aurora. Customers want to migrate to AWS, but there's been some concerns that prevent or stall customers from migrating. This is because many customers can't afford long periods of application downtime for business-critical applications, and the tools that enable minimal downtime are expensive. They are also quite complex, so the whole migration starts to look complex and expensive. Other customers may need a copy of the data on premises, so they need to keep the two databases in sync. Or perhaps there's a desire to migrate away from commercial databases to open source databases as part of the migration. This can be quite challenging for customers who've never been through such migrations previously. For customers who don't have an AWS region in their country, it can be expensive to send large volumes of data across international network links. For many customers, it's simply because they don't have the skills to manage the migration. Let's take a look at the traditional approach of migrating a database to AWS. First, you need to create your AWS account, set up your virtual private cloud in AWS, connect to AWS with a VPN or Direct Connect, shut down and back up your database, transmit the database back up to S3, configure an EC2 instance with the database software, restore the backup, configure the EC2 instance for the application, and finally switch the users to AWS. If you take a look at steps 4 to 9 that I've highlighted in red, that process could take a week or more, and that's completely unacceptable for most customers. Now, there is a better way. Whether you want to migrate your applications to AWS and use EC2, or the managed services, you have to work out how to migrate the databases securely and ideally with minimal downtime. The AWS Database Migration Service, or DMS, allows you to perform homogeneous and heterogeneous migrations between the various databases on the slide here. The migrations can be carried out with Change Data Capture or CDC. This allows the source database to remain active during the migration, keeping your application up and running until the target database has caught up. Let's take a look at how DMS works in more detail. On the left-hand side, you can see the existing applications databases on-premise and the users connecting to that. On the right-hand side is an AWS with an empty database, ready for migration. In the middle, there is networking, where we are using a VPN in this example, but it could be using our Direct Connect option too. To start the migration, we need a replication instance, which is what runs the database migration service. Once that is started, you need to provide the connection information for the source and target databases. Next, you choose what data you want to migrate to AWS. DMS allows you to choose specific tables, schemas, or the whole database. Then sit back and let DMS do the rest. It creates the tables, loads the data, and best of all, keeps them synchronized for as long as you need. That replication capability, which keeps the source and target data in sync, allows customers to switch applications over to AWS at their leisure. This means that DMS eliminates the need for high-stakes extended outages to migrate production data into the cloud. DMS provides a graceful switchover capability. If you have a critical migration or you want to run data replication continuously, then using DMS with the multi-AZ option is right for you. It works just like the previous slide with a single AZ, but if something goes wrong with the primary DMS instance, then DMS will fail over to the secondary and continue the respective migration tasks. This is very similar to how RDS multi-AZ works, if you're familiar with that. DMS is managed through a console, just like most AWS services, but you can also use the API to call or script migration tasks. You can set up a replication instance and task. In fact, you can use as many replication instances, or you can build as many tasks as you need to run on those replication instances. You can also choose the power, speed, and cost of your migration by using the smallest T2 instance or a C4 4x large for complex migrations. Now, for the important rules. You can migrate from on-prem to RDS and EC2, from EC2 to EC2, RDS to RDS, and RDS or EC2 to on-prem. What you can't do is on-prem to on-prem migrations. So there has to be an AWS somewhere in the migration path. I mentioned before that we use change data capture for the migration. It works by capturing the transaction logs from the source database using LogMiner on Oracle database or the row-level bin log on MySQL, etc. This means there is no need for an agent to be installed on the source database. DMS just needs a database connection and will use the native interfaces to extract the data. The transaction changes are sent to the replication instance and kept there when the bulk load phase, essentially select star queries, is in progress. Once the bulk load phase is complete, collected transactions are applied. When that is caught up, then DMS moves into continual apply mode. This means you can keep the source and the target in sync for as long as necessary before failing over to the target. DMS loads the data table by table. There is a default level of parallelism of 4 tables at a time, but it is customizable to fit your needs. For example, on a busy production system, you may only want to do 1 table at a time. You can also split the data from one source into multiple targets. This is useful if you have a data warehouse that you want to extract data from to populate data marts for, say, finance, marketing, and sales teams. Or you could take the opposite approach, taking multiple source systems, such as operational systems on-premise, and extracting the data into AWS to populate a data warehouse. You don't need to take all the data in a given table. You can use a predicate or where clause to restrict the data that you want to bring across. This could be useful to only bring the most recent data to the migrated system rather than bringing all the data, most of which could be archived anyway. When migrating, you can choose to do a homogeneous or heterogeneous migration. For example, you could migrate from Oracle Database Enterprise Edition to exactly the same version and platform. You could also migrate from one version of Oracle Database to another, or even from Standard Edition to Enterprise Edition. You could also migrate from SQL Server to MySQL or from Oracle Database to Aurora. On this slide, you can see all the sources that DMS supports for databases running on EC2 and for databases on RDS. There are a couple of things to do here. The first is that SQL Server, when running an RDS, does not yet support the CDC operations. This means that you can still migrate the database, but it will only be through the bulk migration process. We hope to address this soon. Also, you need to be on version 9.5 or greater for Postgres for CDC support in RDS. These restrictions are not present when running on EC2. The main difference for the target databases for DMS is that we support Amazon Redshift and Amazon DynamoDB. DMS is also very cost-effective with no upfront costs. With the AWS Database Migration Service, you pay for the migration instance that moves your data from your source database to your target database. Each database migration instance includes storage sufficient to support the needs of the replication engine, such as swap space, logs, and cache. Inbound data transfer is free. Additionally, charges only apply if you decide to allocate additional storage for database migration logs or when you replicate your database to another region or on-premises. AWS Database Migration Service currently supports the T2 and C4 instance classes. T2 instances are low-cost standard instances designed to provide a baseline level of CPU performance with the ability to burst above the baseline. They are suitable for developing, configuring, and testing your database migration process and for periodic data migration tasks that can benefit from CPU burst capacity. C4 instances are designed to deliver the highest level of processor performance and achieve significantly higher packet per second performance. They have lower network jitter and lower latency too. You could also use the C4 instances if you are migrating large databases and are looking to minimize the migration time. And speaking of migration time, this example is from the DMS documentation. It is under ideal conditions with everything running on AWS. And given that most of you will have external networks to deal with, your migrations for a similar size database may take longer. In any case, 5 terabytes of data in 33 hours is quite impressive, especially when there were 4 larger 250 gigabyte tables, a huge 1 terabyte table, 1,000 small tables, 3 tables with lobs, and 10,000 very small tables. Not exactly a trivial database to migrate. Not only can DMS migrate your data quite quickly, but it can also do it at a low cost, for less than $10 per terabyte. If you've ever used other data migration products that support CDC before, you will understand that they can cost hundreds of thousands of dollars for large database migrations. So this is a huge change in the pricing structure. DMS can act as a replication migration Swiss Army knife, but it's not a magic wand. Use it for heterogeneous migrations when minimal downtime is required or there is no native solution. Use caution when some tables have large lobs. They will need some care and attention, as will complex data types such as spatial data. Also, if you have a database under high load, you will need to manage the migration task carefully so as not to impact production performance. Don't use DMS if there is a native no downtime solution, such as MySQL replication, SQL Server mirroring, or Oracle Data Guard. If you can take the downtime, then there's nothing wrong with using the native backup and restore process either. Finally, if your database is 5 terabytes or more and you have a slow internet connection, you need to really test the migration to see if it will complete in time. While DMS migrates the data, we are finding more and more people are looking to switch database engines. So what happens if you are converting from one database engine to another? Where does the magic happen? This is where the AWS Schema Conversion tool steps in. Sct supports the migration of Oracle Database, Microsoft SQL Server, MariaDB, Postgres, and MySQL to any of the open source engines. We don't support the migration to Oracle Database or Microsoft SQL Server because both Oracle and Microsoft provide their own tools for the job, and most customers want to migrate to open source databases anyway. Sct also supports the migration of Teradata, Oracle, Netezza, Greenplum, Microsoft SQL Server, and Vertica data warehouses to Amazon Redshift. Sct also supports a Schema Copy function. I'm sure many of you have been in the situation where an old system doesn't have any documentation or even the DDL to create the database. This means the only definition of the database is the live production system. Sct can create an exact copy of such systems to help migrate them to AWS. The other useful feature it has is the ability to make RDS recommendations, including whether you want to use a cheaper version of a database. For example, if you're using Oracle Database Enterprise Edition, but the Schema Conversion tool finds that you are not using any Enterprise Edition features, then it will recommend that you can use Standard Edition 1 or Standard Edition 2 when migrating to RDS. Sct recently introduced a new feature, data extractors, to help migrate data warehouses. This extracts the data through local migration agents and optimizes it for loading into Amazon Redshift. The files are loaded into an Amazon S3 bucket, or you can use Amazon Snowball as an intermediate step. This then allows you to load them into Amazon Redshift in the best and most efficient way. On this slide, you can see what the Sct interface looks like. On the left side, you have the source database information, and on the right side, you have the target database information. In the middle at the top is the list of issues with Schema Conversion tool has found, and below that are the two windows, one for source program unit and the other for target. This allows you to see what the problem is and make the appropriate change. The object that Schema Conversion tool migrates are listed on the far right. This includes all the basic things like tables, index, and view definitions, but also the complex packages and store procedures. Another trick that Sct has up its sleeve is the ability to process your application source code and fix the SQL statements in line. This feature can greatly accelerate applications and database migrations, especially for poorly written applications with SQL code written throughout them. With respect to the Sct, the assessment report is the most important feature. It should also be the first thing you do when you're considering a database migration. Once you connect the Sct to a source database and then select what target database you want, the Schema Conversion tool can produce the assessment report that will list all the issues it found, the number of occurrences of them, and why it's a problem. This is an essential tool for understanding the complexity of a database migration and for assisting with project planning. The Schema Conversion tool is free. Well, it's free for active AWS customers with accounts in good standing, so please pay your bills. Now I'd like to talk about Amazon Aurora that is built upon the RDS platform. So what is Amazon Aurora? It's a MySQL compatible and Postgres compatible relational database platform with the performance and availability of the commercial databases delivered as a migration service. AWS announced the MySQL compatible edition at re:Invent in 2014 and the Postgres compatible edition at re:Invent 2016. If you're going to build a new database for the cloud, then you don't want to use the same architecture that has been around since the 70s. AWS decided to build a new database platform using a service-oriented architecture. The storage layer has been broken out into a separate database-optimized storage service that receives the database changes in the form of log entries, not file system blocks. This is a huge difference and the main benefit of the Amazon Aurora platform. It is integrated with our AWS services to help manage Amazon Aurora, such as EC2, Amazon DynamoDB, Amazon Simple Workflow, and Amazon Route 53. Backups are continuously taken from the storage service and integrated with Amazon S3 with 11 nines of durability. You can also create a manual snapshot and save that in S3 too. This slide demonstrates the large differences between the storage operations of RDS in a multi-AZ environment and Amazon Aurora with the same failover capability. On the left-hand side, you can see the RDS MySQL environment, and on the right, Amazon Aurora. MySQL has a primary instance and a standby instance in another availability zone. You can think of availability zone as a data center. The primary database has the write to an EBS volume, which is replicated by EBS in the same AZ. At the same time, the same write is sent across to the standby and the same write to EBS is applied there. Bin log files and other metadata is also kept up to date across both instances. On Amazon Aurora, there's a primary instance and a read replica. There is no need for a standby instance that can't be accessed like an RDS MySQL. This is because read replicas become failover targets in Aurora. The storage is located across 6 locations in 3 AZs and kept consistent by the storage service. There is a quorum of 4 needed for an acknowledge write and 3 for a read, providing a highly resilient storage tier. Yet, as discussed before, the database just needs to send the log or change information to the storage service and replicate some basic information to the read replica. This greatly reduces the amount of I/O that Aurora needs to do for a given transaction load, increasing the scale that Aurora can handle when compared to RDS and traditional databases. Intel provides a couple of key technologies that help with Amazon Aurora. When you encrypt your database, the Intel AES-NI feature improves the performance penalty associated with encrypting and de-encrypting the data. Intel Turbo Boost technology can help your queries get a boost of CPU frequency for spiky workloads that come into the database too. All the other features mentioned here are available on the latest AWS instances that are built with Intel CPUs. We only have a short amount of time, and there are so many features of Aurora, so I just want to go over a few key features. As mentioned, the storage is highly available with 6 copies across 3 AZs and backups are continuous to S3. With the read replicas operating on the same storage as the master instance, there is minimal lag, typically less than 20 milliseconds. This solves a big problem for MySQL users who often have read replicas that lag into the minutes when there's more than 2,000 IOPS of activity on the primary database. The storage is auto-scaling. It simply adds 10 gigabyte segments as they are needed. The storage service also identifies hotspots and moves data around to maximize throughput and minimize contention. Recovery is single-threaded with MySQL, whereas Aurora does parallel, distributed, and asynchronous recovery that greatly decreases the time that your databases become available after a restart or crash. This is possible because the storage engine can apply the log changes, so each storage segment in parallel. Related to recovery time is survivable caches. When you restart a relational database, the cache is part of the database process, so the data is lost. However, in Aurora, the cache is a separate process that survives a database process restart. This means that when you restart the database, the data is already available in the cache, preventing the surge in disk activity that is normally needed to bring the data into memory before the application can perform at its peak again. Normal databases suffer from such brownouts, as the data is read from the disks into memory. This all contributes to faster, more predictable failover. Speaking of faster, when Aurora is compared with MySQL on the same hardware at scale, it is up to 5 times faster. It should be noted that this is not a single query running, but lots of connections running lots of queries. For Postgres, it's more than 2 times faster on the same hardware. If you would like to know more, AWS has published the benchmark information and how to replicate the MySQL benchmarks on the AWS website. When you are using RDS at scale, it is common to have large instances such as R3 8x large. And with 32 vCPUs, 256 gigabytes of RAM and provision IOPS storage, that's quite a big box. Customers then have the same instance and storage for the primary, standby, and at least one replica. With Aurora, only need one set of storage and a read replica for failover, and can be significantly cheaper than RDS MySQL at scale. When you take into account that Aurora is also faster than MySQL, it is common for customers to find that they can halve the instance size, and then Aurora becomes even cheaper. There have been a series of recent improvements with the Aurora platform that you can read here. I'll call out a few of them. FastDDL allows for adding a new column to MySQL without having the typical table copy operation that happens with MySQL today. Zero downtime patching looks for windows of low activity, suspends the connections, performs the patch, and then restores the connections. This happens so fast that most users would not even notice. Having the T2 small and medium instances available for Amazon Aurora allows you to run your dev test environments and small databases at a much lower cost. Amazon Aurora is now available on all 3 AZ regions, including London, Montreal, Ohio, and San Francisco that were recently introduced. Now I'd like to talk about some of the customers that are using Aurora today. 2/3 of the top 100 AWS customers are using Amazon Aurora, as are 8 of the top 10 gaming customers. It's the fastest growing service in AWS history. Shadi.com is the world's largest matrimonial service based in India. They have 35 million members on its site and wanted to migrate a number of applications and a key MySQL database across to AWS. Shadi.com found that DMS reduced the time to migrate the database by 40%. They also realized a 55% cost saving by migrating to Amazon Aurora. With Shadi.com reducing the time to migrate their database by using DMS, I think it's the appropriate time to discuss more about the actual migration effort. There are 4 basic cases for database migration that have a major impact on the complexity of a given project. If you are just going to lift and shift a database, as is the same from the same platform on-premise to the same platform in AWS, then that will be relatively straightforward. If you decide that you want to switch the database engine and re-architect the application in the process, then that's effectively a new development project with all the associated risks. If you are targeting Redshift, or you want to use ongoing replication, then that has its own set of issues that you need to focus on, such as whether to use DMS multi-AZ and how up-to-date you need the database in the target. The interesting points about this table is that while it contains fairly high numbers for the effort involved with database schema conversion and application conversion, there is also a high number for testing. This is something that a lot of customers forgot to allocate time for, and even for a lift and shift migration, you need to take this into account. After all that, how do you actually use the tools to migrate a database, in this case, Oracle database, to Amazon Aurora? The first step is to use the Schema Conversion tool to connect to the Oracle database and generate the schema for the target Amazon Aurora database. At this stage, you would turn off constraints and indexes to speed up the loading of the data in the next step. In step 2, you would use DMS to start the bulk migrate phase to populate your Aurora database. Once the bulk load has finished, you can then enable constraints and indexes before applying the outstandard transactions. Eventually, both databases will be in sync, and you can cut over to your application to point to the new Amazon Aurora database. If you are interested in learning more about what I've discussed today, you have several options available to you. To gain more confidence and hands-on experience with AWS, watch our instructional videos and explore the self-paced labs. Additionally, you can attend our instructor-led classes by qualified AWS instructors and learn how to design, deploy, and operate highly available, cost-effective, and secure applications on AWS. And finally, remember to validate your technical expertise with AWS certification. This brings me to the end of my session. I hope you found it useful. Do remember to complete the survey by visiting the link on the screen today. With that, I would like to thank you for attending AWS Innovate.